How are you guys doing today? So I hope you had a big lunch and fully charged to understand large language models. Yeah, I think Nirma already gave a lively introduction to me, so I'm going to skip it and dive into large language models. So what is a large language models? So when you think about it, is this the picture coming into your mind? It's a big brain that is connected to multiple servers which are serving all the requests. Unfortunately, it's not the case, actually, because large language model is a function that takes a sequence of tokens as inputs. And then it will generate it will compute a probabilistic distribution, because, and that probabilistic distribution will tell you what would be the most likely token that would come next after this sequence. And that's what actually large language models does, and that's exactly a function. And what this function is a collection of weights. It's not a mathematical, of course it can be represented as a mathematical function, but actually in reality it's a bunch of weights stacked together which are learned during the training process. And this weight will tell, okay, how we need to transform this input sequence into the predicted output token, and that will give the probabilistic distribution of that. And of course, these models, they don't have any state. They are stateless. They don't remember what to chat with them. Of course, ChatGPT does, because that is implemented to the application, not to the large language model. So that's how we actually implement memory into these kind of applications. Okay, so what does these models understand actually? So what's the vocabulary for large language models? So I have actually used the tokenizer and try to break down even the text in this slide using the tokenizer that GPT model used. And you can see sometimes the tokens are words, sometimes they are not, sometimes they are part of words, sometimes they are just characters. So what actually happened is, I think Rani also mentioned this, when we train these kind of models, we are breaking the sequence or the text that are getting to us into multiple tokens, and this process makes sure that we'll end up with a more efficient vocabulary, because if you try to break down everything as words, and when we are training these models, we are training them for multiple languages as well, right? So then we will end up with millions of unique tokens in our vocabulary, because each word can also have multiple forms, right? Based on the context we are using. So that's why we need this kind of a approach, and also this will ensure whenever we have a new word formed using, combining different small tokens, still you can capture that meaning. And of course, model doesn't understand words, they understand numbers. That's exactly why we need embeddings. And embeddings is a step further. It's not just a random arbitrary number that we come up out of thin air. It's actually a vector representation of each token that has a certain semantic meaning, so that when we get a bunch of similar words together, they will be closer to each other in this vector representation. And this vector representation is not 3D, it can be 1,000 dimensions usually, because we have a lot of words you need to capture. Okay. So these vector embeddings tokens, those were there actually for a long time. Even in my final year project, I was using most of these concepts to do certain natural language processing. But it wasn't colorful as what is it now, because there was a huge gap. And that gap was early case, of course, when you look at natural language, to understand the meaning of a certain word, you have to go back and look at other words as well. For example, in this scenario, to understand what it means when you say the animal didn't cross the street because it was too tired, you have to go back and read what it refers to, right? So obviously it means the animal, right? And the models, they are not capable of doing these things when we have longer sequences, because you know, right, with large language models, now we have put thousands of words into the sequence, not just 1, 2, 3 words, right? And we had like traditional models like RNN, LSTM, which we used earlier. They couldn't handle these kind of sequences when they become larger and larger. So because of that, we couldn't do what we are doing right now with LLMs. And what make it possible is attention. And this is a paper that came and which actually proposed the first transformer architecture. Attention is all you need. So this paper proposed, okay, focus on what matters, and also when you look at a certain word, not all the words will matter to that word when you try to interpret the meaning of that word. So because of that, you have to dynamically go and look at all the words and try to figure out how much attention you should give to those words when you try to understand the meaning of a certain word in the sequence. And of course, I will explain how that works. So how that works with large language models is using this mechanism called self-attention. Okay, now we are going a little bit into math. I was trying to avoid that as much as possible, but I think we are okay, right? So what self-attention mechanism explain is, when you try to interpret a certain token in your sequence, you need to have 3 unique vectors for each token. And one vector is the query vector. What this vector does is, it will capture what information this specific token is looking from other tokens. Going back to our previous example, where we have the animal and that refers to, where we had it and that has to correlate with the animal. So if you look at the term it, when you look at it, in our brain, we feel like, okay, this should be relating to or correlating to some thing, right? Cannot be a person, but has to be an animal or has to be an object. So the same information, if you can capture using this vector, then we can make use of that to actually figure out which vectors we can focus on, right? Which tokens we can focus on. And the second vector, so now we know what we need to focus on, but also we need to have a way to represent what this token can offer to other tokens, right? For example, if you look at the key vector for the animal, then you should say, okay, I am a noun, I am an animal, I can I can connect it anything that refers as it, something like that, right? And then we need to have the third vector, which actually contains the information, actual meaning of that word. And when you have all these things, what you can do is you can calculate the attention using this formula. Okay, it has some vector multiplication, dot products, and it does certain normalization. So we end up with something similar to probabilities ultimately. And I will tell what happens in a little bit deeply. So if you consider this sequence, how are you doing? And that has 5 tokens, because I consider words as tokens for this discussion, sake of the discussion. And you can see, for each token, we can come up with each token will have a query key and value vectors, right? And when we have that, that means we'll have 5 vectors for the full sequence from each category. So that can be a matrix, right? So that those are the matrices we have. We have the key matrix, query matrix, and value matrix. And the first thing we have to do is we have to do a dot multiplication between the query and the key matrix. And when you do that, we get this new matrix, and that's the important part. That's the attention. That matrix can give you the information. If you can look at a certain token, for example, let's say I'm looking at the token U, and then I'm thinking, okay, how much the token R is correlated with that. And it seems it's very little, that is denoted with the blue blocks. But if you look at the other direction, if you look at the token R, and that is correlated more with U than the other case. Because of course, when you have R, the only possibility you can have is either plural noun or it has to be U, right? One of those possibilities. But with U, you can have multiple other verbs. And also, it doesn't make sense to relate to a verb when you look at a noun. That's why we have this result. So I think you get an understanding what actually attention try to do. And when you have this information, you can easily build large language models because with that, you can capture where we need to focus on. But the other improvement that we have right now with the large language models, we don't have one attention. We have multiple heads that are parallel running, which captures different information. For example, one head may be capturing the grammatical correlations between the tokens, and other one may be capturing the semantic correlations. Like that, you can capture different correlations using multi-head self-attention. And then if you look at the transformer block, which is actually the core LLM engine. So actually, one LLM model will have maybe dozens or maybe even hundreds of this kind of transformer blocks. And you can see in the transformer block, we have three components, but two of them are very essential. One is the multi-head self-attention. And this is the part where we actually use to help to understand which information we need to focus on from the sequence that we are getting. And then we have the feed-forward neural network, which is not a new thing, which was there earlier as well, which can actually capture nonlinear patterns, do a lot of those stuff. But in simple terms, what it does is, it is processing the information that we found. Okay, this is the information that we need to give attention. And then this layer will process that. Also, it will store some information as knowledge. And that's how actually large language models can answer your questions accurately when you ask about certain stuff, because those information is retained within these layers. Okay. So we learn about the transformer block, but this is how actually we use the transformer block in actual large language models. So this one, the transformer architecture that I have in my right-hand side, is what actually initially proposed in the first transformer paper, where you have an encoder-decoder architecture. Don't worry about the terms if you don't understand. And that architecture proposed, okay, you can have one encoder with n number of transformer blocks, and another decoder with n number of transformer blocks, and then you can basically transform whatever the input coming, and then to a certain output. And this one is not an optimization for language models. That's why GPT models and also the Llama models, they came up with the other architecture, which is an optimized version. They just get rid of the encoder, because the encoder is usually focused on mostly the input data. We don't worry about input data when we are trying to generate content. What matters is the output data, right? And again, this can have a number of transformer blocks stacked together to process the information you are sending to the model. And then there is a softmax layer to the end. This what actually give you the probabilistic distribution that I mentioned earlier, which can actually tell you, okay, which token is the most likely token that could come next. Okay, I hope you understand a little bit about how LLM is architectured. So right now, let's try to learn a little bit about how these LLMs are actually trained. Yeah. So when you are training LLMs, we call it pre-training. And during this process, what we do actually is we get a huge amount of data, massive data sets from internet, books, everywhere, and then use this information with a technique called self-supervised learning. So I think you may have heard about the terms supervised learning and unsupervised learning. In supervised learning, you actually have annotated data. That means you have the input value and also you have an expected label. So you can easily map the relationship between them using a model. But in unsupervised learning, you don't have any label data, so it's going to be a little bit tricky. There you need different other strategies to train your models. But in this case, fortunately, we don't have to go with unsupervised learning because we have a massive data set. It's not going to be feasible to actually label them. But here, fortunately, we have a pattern, because we are actually trying to predict the next token, right? So whenever we have a sequence of text, that means the label is in the text itself. For example, if you look at the diagram figure here, so you can see, if you consider this, the capital of France is Paris, and when you try to get the tokens out of that, also the immediate next token becomes the actual label or the expected predicted outcome, right? So since we can arrange the data set like this, we call this self-supervised learning because we are not going to help the model. The model is already using the data set and doing it by itself. And with this approach, the model will learn how to do the text completion. And again, so when we say text completion, right now, when you because you have used ChatGPT, etc., you may have a different opinion, but text completion means it's not going to answer your questions. It's going to just complete what you said. So, for example, if you say hello, it's not going to give you back hello. It will say, it will try to complete that sentence and say, and welcome to WSO2 Technology Conference. That's what it will do. So, because of this, these models are not going to be that useful. That's why we need other mechanism to actually align the model. This is like we align our vehicles, okay? So now we have to basically go and further optimize this. And this alignment is done through two steps. One step is supervised instruction fine-tuning. And during this step, what we do is, we teach the model using a supervised data set, which has the expected, which has the inputs and also the expected outcomes labeled by humans, not like we did earlier. And then teach the LLM how you have to answer questions, how you have to follow instructions, all those things. And when you do that, only you get this nice LLM that can answer your question. When you say define LLM, it will give an answer. Still, it's not enough because this is like laboratory testing, right? We haven't tested that with humans. Humans may not like it. Or there can be bias, there can be toxic content generation, right? So that's why we need this other step where we get the human feedback and then do a reinforcement learning again on top of this fine-tuned model and then get the more secure, more model that match the human preferences more. And this is the process actually we use to train large language models. And now we have discussed about the architecture and also we talk about how we can train such a model. Now let's see how we can use these kind of language models efficiently. The first thing you may have noticed already is when we are using these models, we are not trying to basically go and load the weights. I mentioned like earlier, the LLMs are a bunch of weights, right? We don't go and load the weights and we don't try to set it up. That we don't have to do. They are already exposed as APIs. There are already existing software that help you to give a common interface to use these models. And that interface defines certain stuff. It say, okay, when you are prompting these models, you have to use a prompt array, which include multiple messages with different roles. For example, they have defined the system role. If you use this role, you can give more instructions to the model. And then you have a user role. With this role, you can add the inputs coming from the user during the runtime. And then you have assistant role, which actually holds the historical generations from the LLM itself. So I will explain how we use this. And also if you look at the diagram, you can see all these things will go through the LLM API, and then only it will reach to the actual large language model. And this is a sample prompt. If you look at this, you can see just a JSON array, and it has a role parameter, and also, each component has a role and also content. The first role is the system role, where we have the instruction to the model. It says, okay, you are a specialized SQL assistant. You can output only raw SQL code. You can't output anything else. So the instruction is very clear. And also then, we have a question coming from the user. How many users signed up last week? So what do you think we will get as the outcome? Will it say, okay, it's 23 users, or let's say it's 100 users, or it will give an actual SQL query, because in the system prompt, it is instructed to do so. And since we have fine-tuned them to follow the instructions, it has followed that instruction to the letter now. And this is the LLM response we got. And assume now we want to do a follow-up question. Say, okay, I'm not happy with this query. I want to say, okay, maybe filter only those who have those accounts that are active. So when you want to do that, LLM call or to the API, then you have to use this kind of a prompt. Now you can see we still have the system prompt again, the same thing repeated, because I said these models they are stateless, right? They don't keep anything in their memory or anything. Then we have the user prompt that we sent earlier, and also the SQL query generated by the model, we send it to the model again, right? And then we have the new user prompt where we say filter that by active state. That's the new modification that I want to do. And you can see the middle part where we have this user prompt and the assistant prompt is actually the past conversation history which I feed back into the model, so the model knows that this is what it did for me previously. Otherwise, it will never know. When you use ChatGPT, this is hidden, because when you use ChatGPT, that is written to the application, so you don't have to worry about this stuff. But when you use the model as API directly, this is how you have to use it. Okay. So now we know how to use these models using the API, but now let's discuss a little bit about the problems or challenges we can face with this model. So the main problem we have is these models, they prioritize fluency over factual accuracy. And that is intended, that is by design, because these models are probabilistic models. They are not databases, right? That you write a query and fetch data. And whenever there is a gap in the information, what they will do is they will make up a plausible lie and present that to the user, which we call as hallucination. So this is the big term, big challenge that we have with LLMs. And to prevent these hallucinations, we need external controls which can actually transform these guessing models into reliable system when you are building any AI application. So the first thing we started doing was to engineer the prompt. That means we write the prompt very nicely so that it instructs the model, this is how you should operate. And with that, you can say, okay, this kind of a task you are going to do, and this should be the output that you send us, and this should be the format. It has to be in markdown format. And also you can say, okay, be polite or be aggressive. You can tell all those things in the prompt and basically regulate the behavior of this model. And these are some of the examples that we have right now. There are a bunch of prompt engineering techniques widely known. The first one is the role assignment that will specify saying, okay, you are a senior Python developer, and basically you review code for the security vulnerabilities. That means when model is responding back with certain review, it has to have only security vulnerability related reviews, right? And in the second case, we have used the few shot prompting. That means we don't write these instructions. We don't waste word with that. We just say, okay, these are a few of examples, and just follow that pattern and complete. So it will learn from the example dynamically during the runtime, and then give us a proper response. And the other one is the chain of thoughts. This was a very common pattern and very famous pattern back then, but now we don't need this that much. So this will tell, instead of trying to directly answer for certain reasoning questions, you need to think step by step. Okay, so we talk about prompt engineering, but now we are telling prompting is just the tip of the iceberg. It's not going to solve your hallucination problems. Actually, the root cause down the hill, right? So hallucinations are actually not due to the prompt issues. It's mostly due to information gaps. And when there are missing information, then only the model will start guessing. And then the obvious answer is, then let's bring in more information to the prompt. That's what we call as in-context learning in these kind of scenarios. But then there are also problems, because when you feed garbage into these models, that's why I say GIGO, that means garbage in, garbage out. When you feed garbage into these models, then what will happen? Still, the model will mix the facts, and then it will start hallucinating. And there's this other issue, because the models also have a certain context window that can hold your information. That's kind of the RAM of the model. So if you put a lot of information into this context, then the context starts rotting. That means, I earlier explained that this model has a certain attention mechanism that is used to focus on the important information, right? That attention mechanism can fail when it has a lot of information. So you have to be careful in that area as well. And that's why we have this new discipline called context engineering. So what context engineering say, you have to design, structure, and optimize the entire information environment to avoid hallucination. So you can't just go and change the prompt and adjust certain words to avoid these problems. Instead of that, you have to consider this as an architectural problem. So you have to basically address this at the architecture level. You have to think about what data you are going to connect to the model, and how you are going to connect them to the model, what's the format going to be, all those things. And then only you can actually solve this problem. And prompt engineering is just a small segment down there. So when you consider context engineering, there are multiple aspects. One aspect is the memory management. Memory management is very important, as I mentioned earlier. These models itself, they don't keep track of what you are going to chat with them. So you have to build that into your application, and then you have to manage that properly. You have to feed that when the model needs it. You can't put all the stuff that you have chat with to the model, right? Like in ChatGPT case, maybe you are using ChatGPT for past 6 months. You can't put all those chat to the next LLM call. That's not going to scale. And that's exactly why you need a proper memory management under the context engineering. And that memory management can include short-term memory as well as long-term memory, because short-term memory is just the past previous few chats. But long-term memory means it can even track who is this user, what's his job, what are his preferences, all those things. I mean, you can go and try ChatGPT and say, okay, write an essay about me, and it will do that to a certain level based on what it knows about you. And then again, the state management. This is very important because we are writing now agentic applications. And these agentic applications, they have multiple states when they're executing certain requests. For example, if you say, okay, go and plan a trip for me, it will start by basically booking certain hotels. And if it forget about which hotel it booked and also the time or whatever, the date, etc., when it's going to the next step, then it will book a cab from a different area for a different purpose, right? So it cannot happen. So it has to keep track of all these stated. Although it's a single, this is a single request. This is not like multiple requests from the user's point of view. But for the LLM, these are going to be multiple steps. So you have to manage those states properly and also feed those information. And then the other thing is the retrieval augmented generation. This is the way we usually feed external information to these models so that we can enrich their knowledge. And this is also very important because what this means is you don't feed all the information to the model. You have to first figure out which information is more relevant to the given question. And only those information you have to feed to the model. Otherwise, when you have millions of documents, if you try to push that to the model, then we will have context rotting, as I explained earlier. And the other thing is, when you have agents, you have tools. That means these tools can fetch more information to your model as well as they can perform actions. So again, this is a very important thing to track. Because if you don't know what happened during the previous tool execution, again, the model will be in trouble and you will not get accurate execution. And of course, down the line, we still have the prompt engineering. You have to nicely tell the model, otherwise it won't follow your commands. So this is the last slide. So what it means for us now. Of course, we know LLM models are probabilistic models that generate content. And that has a new opportunity as well. Because unlike in previous case, there are certain problems that we couldn't solve with writing code, right? For example, if somebody asks you to write a chatbot, then what would have come to my mind is, I have to write like 1,000 if conditions and 1,000 rejects. That's the usual way you could have done if you have used only prompt. And that you can try out still. You can ask ChatGPT and do and generate a rule-based chatbot and see how it will work. But with these large language models, it's a matter of just connecting to LLM and just providing some information, some prompt, and you're done. And it's going to be 100 times better than what you could have built with these rule-based systems. And like that, there are a lot of opportunities. And this shift is referred as a Software 3.0 by Andrew Karpathy. And you may have heard of him. He is a very active person in the community. And what he means is, like in previous case, like when you have 1.0, what we did was we write code, which were very deterministic. And then in 2.0 case, we had neural networks. That means software is a bunch of weights. But now we are in a new era. We don't even have to worry about the weights. We just write prompts, right? We just put information into the prompt. It's just natural language. So that's why we call it Software 3.0. And of course, if you master prompt engineering, context engineering, those concepts, you can do better in these areas. I think we have time for the questions. So you can basically catch up with me. I will be here if you have any questions.